Hi, how are you doing? Right, let's get this going here. Okay, we should get some pictures any second. Okay, hi everybody. I'm just it's David here again. Thank you for joining us for Computational Electrophysiology with Ed Viegmont of the University of Bordeaux. As with our previous webinars, we've had some problems with getting you guys connected for questions. So what we'll do is we'll record as before and without questions. And then if anyone can add their questions in the questions answer box, then Ed will answer these very, very shortly. I'm just going over to Ed now. We will begin our presentation. Okay, Ed, you are now the presenter any moment.
I think now.
There you are.
Hope everyone can see me. Good afternoon. I'm going to be talking about computational electrophysiology. I'm going to assume you remember a little bit of what was talked about before and about action potentials and things, but we'll do a little bit of review, but we won't go as much into the single cell as maybe you need. Okay, and this is the outline of my talk about propagation, extracellular fields, and I'm going to talk a lot about re-entry and rotors today. So what are some of the aspects of computational electrophysiology? What can we do with it? We've been using it to help understand biophysical processes, both normal and pathological. We can also, it's also been used a lot in non-invasive electrocardiographic imaging, as in the whole ECGI is based upon it. We can use computational electrophysiology in device design, both for designing hardware, you know, where do we place electrodes, how big should the electrode be, how much current or how much voltage should we use, as well as algorithms. So once we detect signals, then how do we process the signals and what can we do with the signals to trigger the hardware? For drug design, they're possible to use. We can look at the effects of channel blockage or a particular type of drug kinetics on action potentials, as well as planning ablation procedures is going to become a very important use of models and risk stratification. So let's start off with the heart. And you'll notice that different places of the heart have different action potentials. The action potential, if you recall, is the voltage that's measured across the membrane of the cell. This thing, every switch you make loses your screen. You can see that the action potential, as we know, starts in the SA node of the heart. It travels through the atria, which are the upper chambers of the heart, and then it goes through the AV node, goes down to the Purkinje systems, and then from the Purkinje system, it exits into the myocardial muscle. Different parts of the heart have a different shape of action potential and different action potential duration, so how long this part is. And at the bottom, you can see how the ECG relates to the action potentials in the different parts of the heart. One thing I wanted to know, it's annoys me to no end all the time, even on the cover of Heart Rhythm, you'll see there's these little tracks that are connect the SA node to the AV node. They don't exist. They call them internodal pathways, but it's a bad idea that gets perpetuated. So don't talk about it. So the cell. There's the action potential. So this is if we place an electrode inside the cell and we give a short little stimulus. Doesn't have to be long, a millisecond. You start this process known as an action potential, which lasts for several hundred milliseconds. And what happens when the action potential starts, then there is an influx of calcium. The calcium then triggers the binding of troponin and myosin and actin, and you get a contraction, and you see there's a gradual buildup in the contraction force. The contraction, this green line you see, is actually longer than the actual action potential. So the cell is still producing a mechanical force after the electrical signal is finished. And then I have here this, and it's impossible to trigger a second action potential before you await a certain amount of time, which I call the absolute refractory period. And then afterward, there's a relative refractory period where you can trigger an action potential, although it's more difficult, so you have to give a stronger stimulus. And what's producing the action potential? Well, there's an exchange of ions across the cell membrane. And there's different ions, as if you recall, there's different concentrations of these ions across the membrane. So for example, outside of the cell, the concentration of sodium ions are a lot higher than inside the cell. So if a sodium channel opens, then sodium ions are going to diffuse from outside to inside. Conversely, with potassium, it's the opposite situation where there's more potassium, higher potassium concentration inside the cell than out. So if the channel opens, potassium tends to go the other way. And to establish these ionic gradient differences, we have these active pumps, which pump one ion out at the expense of another ion coming in. This is the basic model of a cell, which an electrical equivalent model of a cell, which we call the parallel conductance model. And the parallel conductance model basically says you have a membrane, which is the membrane has a physical property called capacitance. So it means that it stores electrical charge along the membrane because it's so thin, and that stores an electric field. And it stores energy in an electric field. And then you have channels or proteins inserted in the membrane, and they're represented by one of these conductance pathways. So we have, what I have here is an arrow through a resistor, meaning it's a nonlinear time varying conductance. And then there's a little battery, which represents the ionic concentration difference across the membrane, which produces the potential. And we have, for every different channel, we have a different parallel pathway. So this is for a particular potassium channel, a particular chloride channel, sodium and calcium, as well as we have these, it's a pump there, which represents the sodium calcium exchanger. These things can require ATP, as well as a sodium potassium pump, which I talked about before. And there's a voltage across this membrane, which we call VM, the transmembrane voltage, which is the voltage on this side of the cell minus the voltage on that side of the cell. So here's a modern model of a cell showing many of the components in the cell. We have the pump, we have channels, we have exchangers, and inside we have a storage of calcium. So the calcium storage, the calcium release is triggered from the calcium storage if a lot of calcium is released in a short amount of time. We also have within the calcium causes the binding. And if we look at, for example, one channel there, we see the way it works, and we have a mathematical description of just this one channel. And we have similar descriptions for all the channels in the membrane. And you can see there are a lot of parameters to fit. There's a lot of all these numbers, those are physical constants, but then these numbers and the exponents, these are all numbers which have been fit based upon experimental data. And a pathology might affect one of these changes. So there's a lot of fitting to be done. We have the different shapes of the cell. So what do we get the different action potential shapes? Well, the different action potential shapes arise because there's different currents and different proportions of currents in different cell types. So for instance, atrial cells have more of a triangular shape or might have a dome, whereas ventricular cells are more square shaped. And if you look, you can see that they have the different types of currents that are very different between the ventricular and the ionic and the atrial cells. The cell, we talk about phases of the action potential. So we have the rapid upstroke, which is called phase 0, which is caused by the opening of the sodium channels. There's a phase 1, which doesn't really show up that well here, where it's a rapid sort of depolarization down, which is caused by the transient outward potassium current. There's a plateau region here where calcium, I say calcium here is slightly bigger, but there's also potassium, which is also flowing at the same time. And then there's a rapid repolarization phase 3, which is when the potassium channel, the potassium currents overwhelm any calcium or sodium currents and return the cell to the resting level, which we call phase 4. Again, modern ionic models allow us to to keep track of many things within the cell. Even modern models now have mitochondrial representation, which adds a lot of complexity to the model. Again, you have to pick the model that suits your level of detail that you require. Maybe you just require propagation, or maybe you are looking at the effect of mitochondria on channel function or arrhythmia development. So these are what they call the third generation models. They become less phenomenological and more mechanistic as they try to incorporate as many different known processes as they can in the cell. Again, metabolic and fourth generation, instead of just Hodgkin-Huxley channel models, we talk about Markovian models. And so you have a large number of increasingly stiff ODEs, easily on the order of hundreds at this point. And that little space is very important. That can determine the whole cell. What happens in a few milliseconds determine what happens in the cell. I'm just gonna point out this resource called CellML. CellML is a repository of ionic models. It's written in a markup language called CellML, and you can download and upload models there. You need some sort of tool to be able to actually write or run these cell models. So there's a tool called OpenCore, which is freely available. Another one called JSIM. And these will then take the CellML models, convert them into a set of ODEs, and then allow you to run the cell models as well as investigate any variables within the model, how things change over time. You can stimulate them at certain frequencies or give them certain protocols. And then there are some tools, and you can even incorporate them to produce C++ code or C+ code so that you can then put them into your own simulator. You have to be a little bit careful though, because models don't always work as published in the paper. Either there's a mistake in the paper, which happens all the time. People make curves, and then they change the model a bit, and they get new curves, and they forget to update the model in the paper. And so the worst thing you can ever do is take a paper of an ionic model and then try to enter all the equations by hand. You're just in for an unpleasant experience if you try to do that. So what's one of the problems with ionic models? Well, there's many problems why we don't always, they don't always behave as well as you would like them to behave. They don't always correspond to what you measure experimentally. First of all, you can never get all the currents from a single cell. It's just impossible, and the currents vary between cells, so that's problematic. And then again, cells have this variability. So if I go from one part of even though if I'm doing atrial cells, the cells, 2 centimeters apart might have differences, or even cells next to each other will have slight differences. So which makes people either try to model a typical cell with sort of the average properties, or they take a population approach and they simulate the behavior of a population of cells. These models, there's many parameters to fit, like I say, thousands if you look at a complicated single cell model, and we don't always have a good way to measure all of these parameters. So we have to do fitting. And really, we can measure kinetics of the cell channels well. So we can do patch clamp experiments if we have a channel blocker, or we can do single cell if we get single channel if we're lucky. And so we can see how the channel opens and closes in time. We can know that very well, but we really struggle to actually determine how many channels of a particular type are in a particular cell. And like I said, if we try to measure 2 cells, we're going to get 2 different, the kinetics will be the same in each cell, but the quantities in each cell will be different. So we can never know that. Again, we can only gauge the total current by fitting things at the end. You also damage your cell. To do these experiments, you have to measure the currents in a cell. We have to isolate them. When you isolate the cells, you damage them. And then we ignore all this non-electrical processes, all these biophysical pathways which feed into each other and affect the channel operation, but we don't put them in our model. So there are some approaches to get better fits for ionic models. So we can get the kinetics of the models, and then that leaves us the only thing to fit being the magnitude of the current. And if we choose the magnitudes of the current correctly, then we'll get the proper action potential. Some things to do, people have tried genetic algorithms fitting both voltage and calcium over a range of frequencies. That helps. Fitting the membrane resistance, again, something else to fit besides just voltage waveforms. And finally, using exotic excitation pulses to try and isolate particular currents. So what does the tissue look like? This is sort of the schematic of a more realistic looking piece of cardiac tissue. You'll notice cardiac cells, they have lots of connections to each other. It's not a regular brick-like appearance at all. The cells have, are bifurcated at points, have little things that jet off, and there's not really any side-to-side connections. There's all the connections, these squiggly lines, which we call the intercalated discs, are really where the cells do all the communication. Because you can imagine cells move, and if things aren't exactly rigid when they move, then structures will get ripped apart. So if we can look into some detail at these gap junctions, we'll see that actually, lose it again, or not. And you can read my mail while you're bored. You can see that between the cells, it's not a line. It's actually quite an undulated pattern. So it's not a straight. From many photographs, you think it's just straight across, but it's actually quite a wavy. There's actually quite a lot of surface area. It increases the surface area greatly between two cells. So this is cell 1 and that is cell 2. I hope you can see my cursor. I'm looking in the upper right corner, and you have a bunch of proteins, some anchoring proteins that keep these cells close together, and then we have gap junction. So what's a gap junction? Well, a gap junction is formed of something called a connexon, which we see in the lower left A, and the connexon is the basic building unit. The connexin is a protein, it's the basic building unit. 6 connexins come together to form a connexon. A connexon has a central pore to it, and it has these, which may or may not be the same, identical to 6 connexins, so 6 connexons. And so a connexon is found in a cell, and a connexon in one cell then sort of connects to a connexon in a second cell to form a gap junction. And then we have a pore that goes directly from the inside of cell 1 to the inside of cell 2. Again, and then so when we look at between cells, the gap junctions, we have many channels. We have these things called desmosomes, which are giving the mechanical stability, as well as the electrical connectivity between the two cells. And there's different types of connexins in different parts of the cells, use different types of connexins. The different connexins have different properties. So there's 43 is very common in the ventricles, 45 in the Purkinje, which is a large conductance with more speed, and in the left atrium, 43, 40, and 45. In the SA node, you find connexon 30.2 as well as the AV node. So these are the gap junctions. They basically allow it's an electrical pathway between cells. So when we have propagation in a cell, for example, we have blue, we have current. If excitation is going left to right, we have blue current from the cell that's firing into an adjacent cell downstream, which is not firing. And then current enters, and it has 2 ways to flow. It either flows out through the membrane or it flows into the next cell. And there's always a question of how robust is propagation in the cell. And for that, we come up with a concept called safety factor, which I'll talk about later. So that, again, we go to, this is very, you don't get a much simpler representation of a cell membrane than just a resistor in parallel with a capacitor. So we're assuming this for this investigation for low amplitudes, the membrane is not active, it's just a passive resistor. which we call RM, and there's a CN. So, and then you connected RGJ is the gap junction. So this is represents current flowing in from the upstream cell, and then we have the red arrow for the current flowing to the downstream cell. And there's a voltage across. Of course, the capacitor has a voltage across it. And then there's a current which flows out of the membrane, IM, which is the net current flowing out of the membrane. And if we balance it, you can look at it in the bulk representation, IN minus I out. So the in minus the out has to be IM. It's equal to the current flowing through the capacitor plus the current flowing through any ionic channels, which RM represents. And we can write that in a differential form up at the top, which just says what's the dot product? That's the divergence of the gradient of the potential scalar field is the current density at that point. So what does current look like flowing across the membrane? Well, if we just take a simple case where we have a plane wave traveling from the bottom of the sheet to the top of the sheet, and the black trace is the VM. So this is a point at the center of the sheet. As simply passes, the transmembrane voltage goes from about minus 80 millivolts to plus 20. The total current crossing the membrane is the blue curve, which is simple biphasic curve. The current flowing through the ionic channels is the green curve. And then the difference, obviously, it has to be the capacitive current. So this is the IC, then has to be the derivative of VM because the capacitor across it. So how can we use this to calculate how safe this is? Well, the current flowing through IM, we take this as the ratio of the current flowing through IM during the upstroke of the action potential versus Q thresh, which is the charge needed to excite a single cell. And if we integrate this current IM, that gives us the charge of this black area, and divide that by the net current, by the minimum current for an isolated cell, or a charge to cause an isolated cell, by an action potential, that gives us our safety factor. And we've been actually able to use this expression even experimentally. And we find that in basic range, it's between, most of the time it's less than 5, which isn't surprising that you would not have a lot of extra charge. And there's also 1.2 when you're doing your sort of related to safety factor, that if you want to start a propagation in a piece of tissue, then you need to excite a certain volume of tissue. You cannot excite a piece of tissue by exciting one cell, or talking in experiment simulation terms, you cannot excite your grid of tissue by exciting one single node of the mesh. You can raise it to like 1,000,000 volts. It will not propagate. You need to start this process, which generates enough current to be able to excite the downfield, the downstream neighbors. So to describe the electrical activity of a piece of tissue, we'd always refer to the bidomain. A lot of people refer to the bidomain equations, which Leslie Tung wrote about in his PhD thesis in 1978. And what does the bidomain equations, what do they assume? They assume, one, we have two domains. We have an intracellular and an extracellular domain. So we have a space that's inside the cell and a space that's outside the cell. Then we assume that these spaces, these domains, are separated by a membrane, and that these domains exist everywhere, are continuous and interpenetrating. So what that means is we actually say within a certain volume at any one point there is an intracellular space. That point is in the intracellular space and in the extracellular space, which we know really can't exist because the points can only be inside or outside the cell. But we sort of play this game where we say that these two domains sort of they interlap with each other, interspersed, so that they exist everywhere. And then furthermore, we say that current leaves one domain and enters another. So current can't be destroyed. So if it leaves the extracellular space, it has to flow inside the cell, or if it flows out of the cell, it flows into the extracellular space. And then we have to, what we call, homogenize the cell. So instead of working with a discrete cell, we sample a volume and we get the properties over the volume. And then we say that's constant everywhere in space. So we homogenize over the intracellular domain, which basically we take the intracellular domain, define and you have to choose the volumes large enough so that properties are constant, meaning that you have to do, the volume you homogenize has to be greater than a cell. It should ideally contain several cells. Even though this is the most sort of complete, it is an approximation of describing the electrical activity, but it's still not a set of discrete cells. So when you really come to a really fine scale, you're going to run into problems, again, related to this homogenization issue, where you're really not sure if you're getting the right solution when you go less than a cell length, because if you take a volume that includes a different amount of membrane in another part of the cell, then you obviously those two volumes are going to react differently. But in the bidomain, you treat everything as having the same. So here's a graphical representation of the bidomain. It assumes that we have an extracellular space, which is a linear medium, which is basically just a resistive medium, so that if you put it in voltage or charge, it would just flow through, using basic resistor rules. Likewise, for the intracellular space, the same thing applies. We have a linear medium. However, connecting the two, we have these little pieces of membrane, which we have drawn in green. And these membrane, it's the membrane nonlinearities which make things interesting. And the bidomain equation sort of can be rewritten most often into two equations. The one at the top is we call the parabolic equation. It's called parabolic because it has first order time derivative. It's not obvious when it's written like this, but in the IM term, we have a first derivative for the capacitive current, dV by dt. So that makes this equation parabolic. And for the second equation at the bottom here, this is an elliptic, and there's no time derivative with this equation. So it actually makes it a bit more difficult to solve. So what happens when you inject cell extracellular? How come extracellular stimulation works? And it works for this reason. So if we have an anode, the positive terminal of a battery, and a cathode, the negative terminal of a battery, current then is going to flow in the extracellular space, which we call O for outside. However, some current is going to want to flow inside the cell. So the current will then flow from the outside through the membrane into the inside of the cell to then produce this component called II. And then when we get to the end, the current II then leaves and goes down and becomes extracellular current, IO. And anytime that current crosses the membrane, it produces a voltage change. And if we remember that simple model I had of the membrane, now we just forget about the capacitor reason. We just have a membrane. Vm is phi I minus phi E. So as we look at under the anode, voltage current will flow from outside to inside, meaning that this part of the resistor will be, the top of the resistor will be positive compared to the bottom of the resistor. So that means that will be and when you subtract this from that means you get a negative voltage change under the anode. In the middle, not much voltage change, but then under the cathode, you get a depolarizing. So you're going to get stimulation under the cathode. Under the anode, you're going to get hyperpolarization. And you can actually talk about a generalized activating function. I think I've talked about it before. And the important part to know, if we ignore a lot of the other math, is that it's the second derivative of the extracellular potential field which determines how strong the response will be, because the extracellular, this IO term, is actually the first derivative. And if that's constant, then it means it's not changing and no current is crossing the membrane. But if IO is changing the extracellular current, that means current has to be crossing the membrane to change it. So that will lead to changes in the membrane voltage. Or likewise, if you can have a constant field, but if your conductivity tends to change, you can also get changes. So how does this tie back to our bidomain? Well, at the beginning, well, not even that long ago, until the 1990s, people thought this is the anode. Under the anode, you get what I talked about, you get hyperpolarization, which is the black color. But then when they actually looked at it, they saw, and it was predicted by the bidomain equation, it's what they call a dog bone pattern. So we have, under the anode, we have the true anode, the depolarization, the hyperpolarization, but also we have this depolarization. And where does that occur? Normally that occurs at the cathode. So they called it a virtual cathode because it was a depolarizing influence. And this dog bone actually occurs because of the unequal anisotropy tissue ratios, meaning that as the current spreads out in the intra and extracellular directions, the ratio of the transverse to the longitudinal conductivity is different. So as the current spreads out, you start to get this voltage difference that magnifies, and it results in these, what they call the virtual electrodes. So again, you need unequal anisotropy ratios to get that. So there's four possibilities then how you get to stimulate a piece of tissue. So when you have, if I apply an anode and a cathode, so I applied my two terminals of my batteries, for example, to a piece of tissue, we can get either something happening at the anode or something happening at the cathode, and we can get something called a make excitation or a break excitation. So the make excitation occurs when I turn on the stimulus. So if I turn on the stimulus, you can see that at the cathode, I would get cathode make. At the anode, when I turn on, well, in this case, you would not get anode make, it'd be impossible. And you get a break if you get the excitation when you turn off the stimulus. And this is the example that I'm showing in this graph below that. You see the depolarizing influence down to about 100, well, minus 200, I think, millivolts. That is what happens when the stimulus is turned on. And then when you turn off the stimulus, the membrane voltage rises back up to rest, but then it continues further and becomes an action potential. And it's because you basically lower the system changes, and you remove inactivation from sodium channels, and you set up a situation where a bunch of currents then fill up the void when you turn off the excitation, and they serve to excite the cell, and they can actually push it over. So you can get, so if we look at the anode here, so this is the anode in B. So you can see that if we turn on the anode, we can get, so this is happening at the anode, so we can get anode make from our virtual cathodes, or we can get anode break when we turn. So if the virtual cathodes weren't strong enough to stimulate the tissue, but if we had but when we turn off the stimulus, then the currents rushing in would then excite the tissue under the anode. That would be called an anode break. And conversely, at the cathode, you can get cathode make because this, well, just reverse the colors that you see in B, and you can also get cathode break from the virtual anodes created at the cathode. And again, this is how complicated you can get. So this is what happens. It's common in experiments. People put on 9-volt batteries to start hearts fibrillating. And if you actually look at the excitation pattern, it's actually quite complicated. So you can see the plus and minus referring to the poles of the battery. And based upon the fiber curvature of the heart and the development of virtual cathodes and anodes, you get a pretty complex activation pattern, which would have been entirely unknown 25 years ago. So, but the biodomain is a bit complicated to compute. So people use the monodomain because it's a lot faster. Again, we're assuming equal anisotropy, where the difference between the conductivity scale tensors in the intracellular and extracellular domain is just a simple scalar conversion, which is not true. And if you do that, you can simplify the monodomain equation to this. Again, it's one simple parabolic equation. However, it has its limitations. You can match speeds exactly along the three principal directions, but not on the off-axis direction. So you can match it in X, Y, Z perfectly, but you can't get it in like anywhere up to the corners. You can't use the monodomains to solve for extracellular potential directly. You cannot take into account bath loading effects or stuff. Okay, we'll stop here. And you cannot use the monodomain to calculate virtual electrodes, so you won't see the virtual anodes or cathodes, but it's way faster. So here's an example. If you look on where sometimes bath loading can have an effect. So here's a movie, the exact same, except that one of them takes into account the bath. And you can see the effect of the bath if you look on the right side of the sheet. Well, one of them, the simulation is going to stop, and the other one will keep going. You can see that due to the bath, you get faster propagation along the surface, and then you get this, instead of having a flat front, you get an accelerated front along the edge. And so that's just to tell you, this is just to demonstrate that, especially with re-entry and things like that, you can get different effects when you use different methods. Well, not methods, but if you don't take this into account, with subtle effect, it can have a big difference. Okay, so the thing we'll do too, in models is you have to adjust your propagation velocity. And there's two ways to adjust propagation velocity. The first way is you can change the sodium current. That's the excitability, which affects the safety factor, which I talked about before. So if you reduce sodium, you're reducing how robust your propagation is, so you get more propagation failure. It affects any extracellular potentials that you develop, especially the del phi E by del T, which is actually useful because people can measure that experimentally for you. And we know that these relationships hold where the second derivative of the extracellular potential is related proportional to the propagation velocity, and the propagation velocity is in turn proportional to the square root of the cube of the peak sodium current. The other way you can affect propagation to control propagation velocity is by changing the conductivity tensor. And there we clearly know that the conductivity is the velocity is proportional to the square root of the conductivity. So if you want to go twice as fast, you need 4 times the conductivity. When you do that, however, you don't change your derivative, and but you should know you're limited. So when you're doing your model, I think you have to figure out there's these 2 ways to adjust your propagation velocity, and you have to try to best match what you know in experiment. If you can match the d phi E by dt, that would be great. And you can increase the conductivity up to a point, but seawater is 1 Siemens per meter, and you really don't want to go much above that. So in solving for extracellular potentials, there's several ways to do that. You can solve the bidomain, which works. It's 10 times more expensive than the monodomain, uses up more memory, really slows things down. It is probably the more accurate one. However, if you only want, there's another way where you can only solve the monodomain, but only solve the elliptic equation when you want to do output. You get almost, it's still a monodomain solution, but you get a much more accurate extracellular potential. Or you can do phi E recovery, where you can calculate this integral where the transmembrane current times 1/4 pi sigma r. And that works for a few points. If you have many points, then that can actually get a bit, actually not too bad. If you store it, it's okay, but if you calculate the 1/r every time, it can become quite burdensome. An alternative approach to try and also sort of a nifty approach relying on reciprocity is called the lead field approach. So if you have the heart and you want to compute the ECG, you can make use of this concept called the lead field. And the lead field is the relationship between the current density at a point and the potential it produces at a lead. So you see all the blue arrows, those are all current densities. And our lead field is our potential difference between where the two wires are making contact with pretend it's a heart. And to produce the potential, that lead, the potential in the lead, so it could be, lead 2 from an ECG, is the gradient of the lead field dotted with the gradient of the voltage. Well, the gradient of the voltage times the conductivity is IM. Well, is the current density by definition. And so the question is then, how do we figure out this lead field? And there's actually, it turns out to be a simpler problem than it looks, because we can solve reciprocity. Because the heart itself is a linear object, linear medium, because it's just a resistive. The membrane is nonlinear, but the conductivities are all linear. So if we apply this relationship, because it's just an impedance, if we apply a voltage source and measure current, we can do the opposite and apply a current source and measure the voltage. And if we do that, then we can solve, and we solve for this potential, and actually that potential turns out to be our field that we want, Z. So this is more of a practical problem where we apply, if we want to solve, for instance, if we want to do a computation and just solve what lead 2 is on our ECG, then we can apply a unit current source across our lead 2 electrodes, measure the potential field that results. So we solve this once, the potential field, and that potential field is also our field of Z. And then that gives us now the relationship between the current at every point inside our heart and the voltage at each lead. And we can just sum them up to figure out what our ECG is. And it's computationally a lot quicker. Okay. And so what is one of the things is, let's refresh what restitution is. So if we have an action potential and there's an absolute refractory period where no matter how much I stimulate in this blue absolute refractory period, I won't get another action potential. If I give a stimulus, I get a little one. If I wait a little longer, then I get a bigger response. If I wait longer, bigger, wait longer, bigger. And we can, by this method, we produce something we call an APD restitution curve, an action potential duration restitution curve. And it's a function of the time from the absolute refractory period. And that's very important, we'll see, for rotors. And likewise, besides not just there's also a conduction velocity restitution curve, exact same idea. However, the curve tends to be a little bit more steeper. It seems to be flat for longer diastolic intervals, and then has a much sharper knee where it starts to reduce, unlike this, which can be a lot more gradual. So we also need to know, we've talked about rotors, talked about phase. So what is phase? Phase is a way to sort of represent time when you have a cyclical event. So for instance, we have these potentials here, which are recurring. There's a cycle, however, the cycle length may vary, but we don't want to talk about time per se, but because this is a cyclical event, we always, you know, you want to talk about it halfway through the cycle. We can convert this to a phase, and then we convert each cycle between 0 and 2 pi. And the simplest way to do that is use an overtransform. So now we can talk about phase and what phase is a point of the heart. For example, here's a reentry, and we see voltages, and we use the Hilbert transform, and we convert them to phase. And I always like to use phase maps where minus pi is the same color as pi. Otherwise, it doesn't make sense. And the black line is, I think that's pi over 2. So you can see how the phase progresses. For 0. So phase mapping, what can we tell about phase mapping? Well, we can tell focal activity. How do you tell focal activity? Because there's a single point, and then you can draw a contour around it and get like one phase. So you can then think of the phase progression. So as we go from the focus, so this is just one part of the heart that decided to spontaneously fire. As we go away from that point, we go through the phases of the phase progression. That's to be contrasted with a reentry pattern, where if we go to a point, and if we have a rotor or reentry, then we get a point, and we find all phases around that particular point, and we can't really say what phase is at that point, because if we extrapolate, we see all phases within an immediate neighborhood of it, so we can't average it or do anything. It's just called a phase singularity. So how do we get rotors or reentry? Well, this is a simple reentry. This is called an anatomical reentry, where we use an S1, S2 protocol. And we're going to see up on the right side, we're going to get a premature stimulus, which will block it. So if you remember the refractory periods, we have to time this at the right location, so that this part is refractory and the bottom is not refractory. And then when we stimulate it, activity will be forced to go to the bottom. So we go up, we wait for things to recover, we apply it, half recovered, half not recovered tissue, and we get reentry going around. So this type of reentry was shown in slices of jellyfish at one point by George Mines. He could poke them and start a wave of a mechanical contraction, and it would go around the same thing too. Then there's another way to start a reentry is by cross shock. Again, there's no anatomical, there's nothing in the middle that stops it from propagating, but we are going to apply the shock, and that went really fast for some reason. They're much more reasonable, and that's what our classical definition of a rotor is. So if we go back here, as we go down, 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 we give the cross shock here. So, what are you doing to me? Again, I wanted to get to the point, see if I could get this. So at this point, we give the cross shock. This part is refractory. To the right, it's recovered tissue, black tissue. It's refractory. So if we stimulate it, we drive it deeper into refractoriness, and then it's going to form a core about which the propagation. So what do all these? I keep on using these terms. What do they mean? So reentry. So reentry is a general term for activity which perpetuates by surface movement. And I'm not saying it's a rotor or anatomical, but just something that rotates around. That is reentry. There is functional reentry, which is reentry around an inexcitable core. So if you have a dead piece of tissue or a scar or a hole, then that's functional reentry. Then you have rotors. So it's 2D reentry, where the core is excitable, but you have a phase singularity. And then in 3D, you can't really talk about rotors. You should really talk about scroll waves. So instead of a phase singularity being a point, then you have a line of phase singularities. And then sometimes you might hear people talk about micro reentry. And micro reentry is a reentry so small it appears to be a focus. Whether or not they exist, we don't know, but people theorize they exist. So you might think you might have a tiny rotor spinning around, and there's only one exit point for it from a structure, and you see that activity pop out, and you think, oh, that must be a focal source. But no, maybe it's a little reentry that only exits once in a while. And how do you initiate reentry? Well, we saw some ways to initiate reentry. We could do a cross-shock protocol. We can, instead of doing a shock, you can create a temporary block. So you just stop propagation, and then you let it relax after 100 milliseconds instead of having to shock it. It's the same sort of thing. You can do rapid single site pacing. I'll show you. You don't have to do S1, S2. It can just be S1, S1, S1. And finally, or you can start from a reentrant condition. So you think if you just pick a central point and pick all your voltages around it in a circular pattern, then you can, it will start a reentry as well. So here's just like they do in the clinics. In the clinics, when they initiate reentry, they do it from single site pacing. Here we're going to do single site pacing from the left pulmonary vein. So it's the upper right pulmonary vein. Pace once, twice, 3 times, 4 times, 5 times. Now we have a reentry. We stop pacing, and we have a reentry that is developed. So with every pace, these heterogeneities develop and grow, and then eventually, this doesn't work with every situation, but that's what they do clinically. It doesn't always work in the simulation, but it always works in the clinic. So let's look at a rotor. What's happening at a rotor? Rotors are sort of complicated things. It took people a while to figure out what rotors were. So at the X, you see we have the phase singularity of the PS. We have a gray area in the middle, which we call the inexcitable, which is called the core. The dashed line is the wave back, and the solid red line is the wave front. So in between the wave back and the wave front, you have the excitable gap. So one way to stop a rotor is to stimulate the excitable gap. If it doesn't have an excitable gap, then it has nowhere to go. And you notice that the curvature of the rotor changes. It increases as we go spiral in towards the core. And if you look at the bottom here, we see what does curvature mean? Curvature means that when you have low curvature, and this shows the wavefront at 2 different times, that the wavefront doesn't really change in size, which means that cells in the wavefront are only exciting, like one cell in the wavefront only has to excite one cell ahead of it. So there's more current. On the other hand, if you have high curvature, then as the wavefront propagates, the wavefront gets bigger. That means that a cell has to excite 2 or 3 cells ahead of it. And then that means that it's going to take longer to excite, and it might break down, but at a minimum, it will be slower. And we see there, when we look around the rotor, as we go from the outside to the inside of the rotor, the action potentials get shorter. Well, the APD decreases, and the conduction velocity decreases. And you reach a point when you go with tight enough curvature, we're at the phase singularity, and we're getting propagation failure. So in the gray area, the resting level is about -50. So the tissue is not recovered. And because there's always all this current flowing across the core can never there's always current flowing. So the core never gets to recover its excitability, and it will never fire an action potential, unless of course the whole thing moves. So the stability of this, So the stability of the rotor depends upon the restitution curve, which I showed you before, the APD restitution curve, whether it's lower or greater than 1. And if we look at, here's an example. So again, how do we defibrillate? You can start a rotor and hope it breaks down. You can add enough physical heterogeneity where a rotor, simple rotor will break down, or you can use an S1 with a really strong S2. I'll show you all these. One thing to note when you're modeling fibrillation is that it's a chaotic process. So that means the slightest change in anything, whether it's discretization time step or ionic model implementation or, I don't know, numerical method, will lead to changes which grow exponentially over time. So so if you compare side by side, two fibrillation simulations, and there's a slightest little change difference, they're going to look very different, even though it's an insignificant change. And you have to look at the statistical behavior, things like the number of filaments, the length of the filaments, and the lifetime. And so, okay, this is promising you. If you put the slope greater than 1, what happens? We start our reentry, our rotor, things start colliding and breaking down. And then very quickly, we get more and more, and we get a big mess. And that's probably not very accurate, because when they map human fibrillation, it really doesn't look like that. Another way to start reentry is to give it a big electric shock. And again, so we give it an electric shock, that's the S1. We wait some time, wait till it starts to recover. And then boom, S2. And you can see that you start getting very irregular activity. Again, just because the field stimulus is so heterogeneous because of all the fiber curvature and all the different states of excitation, you're pretty much guaranteed that that the excitation will be complicated when it starts. That's not to say that it might not settle down into a regular fibrillation, a regular rotor fixed later. Or finally, if you add heterogeneity, like you'll see islands of reduced APD, for instance, at the, you can sort of see it on the right side already. This is a model of the atria, a very old model, but just demonstrates, and they have different regions. You'll see some of them repolarize quicker. And then you'll see the activation pattern is constantly changing. You can even change direction from one cycle to the next. So again, if you want fibrillation, there's a few ways to do it. So finally, just some thoughts about, there's so much more to electrophysiology that we still have to do. So really, if you look at integrative heart function, membrane voltage changes calcium, which changes the way the strength of contraction. The strength of contraction deforms our cardiac geometry, which then opens up stretch activated channels, which change the membrane voltage, causes blood flow. Blood flow depends upon your systemic and pulmonic loads, which changes how your heart deforms. Again, all these things are leading back to each other. You have baroreceptors that activate nerves, which then feed back into the heart to alter membrane. So I think we're quite a ways from this yet. We sort of have things coming into place, but there's still a lot we don't know. We don't know all the levels of feedback and all these things. But this problem is will keep us modeling for quite a while. And I think to be a good computational electrophysiologist anymore, just what you need to know is you have to know the system that you're modeling. You have to know the underlying physiology and biophysics, numerical methods, how to operate in an HPC environment. We're still not, well, for a lot of problems, not at the desktop level. And a little bit of signal processing never hurts. I think you need to be good at innovative analysis. You have to know some sort of language program and something like Python, or people like MATLAB, good visualization skills, patience. And I think very important is that you have to be able to talk to clinicians and experimentalists, both of them. You have to be the bridge, because you know what the models need, but you need to know what to model. You need to know what is the clinician seeing, what is the experimentalist seeing, how does that relate to what I have in my model, and how can I implement it? And then how do I translate those results back to the people? And finally, I don't think anymore you don't need a large-scale programming knowledge. I think there's a lot more. They're becoming too sophisticated. Gone are the days when you can expect a grad student to write their own simulator, but they have to know all the other aspects, which is just as challenging. And I will stop it there. Thanks.